Hi, in this video we're going to do some approximate calculations using the central limit theorem. We're given that xn is the number of gadgets produced on day n by a factory, and it has a normal distribution with mean 5 and variance 9, and they're all independent and identically distributed. We're looking for the probability that the total number of gadgets in 100 days is less than 440. To start, we can first write this as the probability of the sum of the gadgets produced on each of the 100 days being less than 440. Right? Notice that this is a sum of a large number of independent random variables. So we can use the central limit theorem and approximate the sum as a normal random variable. And then we'd basically, in order to compute this probability, we'd basically need to standardize this and then use the standard normal table. So let's first compute the expectation and variance of the sum. So I'm going to actually sum up from 1 to n instead of 100 to do it more generally. So the linearity is preserved for the expectation operator. So this is the sum of the expected values. So, and since they're all identically distributed, they all have the same expectation, and there are n of them. And so we have this being n times 5. Okay. For the variance of the sum, it's also the sum of the variances because of the independence. And so they're identically distributed. So we have n times the variance of xi, and this is n times 9. Okay. So now we can standardize it or make it 0 mean and variance 1. So it's going to be, to do that, we would take these xi's, subtract by their mean. Right? So it's going to be 5 times 100 of them, so it's 500, over the square root of the variance, which is going to be 9 times 100 of them, so it's going to be 900. Okay, so that's going to be less than 440 minus 500 over square root of 900. Okay, so notice what we're trying to do here is, notice that the sum of xi's is a discrete quantity. Okay, so it's a discrete random variable, so it may have a PMF like this, right? Okay, and we're trying to approximate it with a normal density, right? So this is not drawn to scale, but let's say that this is 440 and this is 439. Okay, basically we're trying to say what's the probability of it being less than 440? So it's the probability that it's 439 or 438 or 437, and so. But in the continuous case, a good approximation to this would be to take the middle, say 439.5, and compute the area below that. Okay, so in this case, when we do the normal approximation, it works out better if we use this half correction. Okay, and so this, in this case, probability, let's call z the standard normal. Okay. And so this is approximately equal to a standard normal with the probability of standard normal being less than whatever that is. And if you plug that into your calculator, you get negative 2.02. Okay? So now, if we try to figure out what this, from the table, we'll find that negative values are not tabulated. But we know that the normal, standard normal is symmetric, and so if we want to compute the area in this region, it's the same as the area in this region above 2.02. So this is the same as the probability that z is bigger than 2.02. Okay? That's just 1 minus the probability that z is less than or equal to 2.02. And so that's, by definition, phi of 2.02. And if we look it up on the table, 2.02 has probability here 0.9783, and we can just write that in. That's the answer for part A. Okay. Okay, so now for part B. We're asked, what's the largest n approximately so that the probability, so that it satisfies this, right? So again, we can use the central limit theorem and use the similar steps here. So that we have, in this case, through n greater than or equal to 200 plus 5n, okay, and standardize. So we have, okay, we'll have to n, and the mean here, this is where this comes handy. It's going to be 5n, and the variance is 9n. It's greater than or equal to 5n's will cancel when you subtract. So you're going to get 200 over the square root of 9n. Okay, and we can again use the half approximation here, half correction here, but I'm not going to do it to keep the problem simple. And so in this case, this is approximately equal to the standard normal being greater than, probability of the standard normal being greater than or equal to 200 over square root of 9n. And so same sort of thing here, right? This is just 1 minus this. The equal sign doesn't matter because z is a continuous random variable. And so we have this here. And we want this to be less than or equal to 0.05. Right? So that means that phi of 200 over square root of 9 has to be greater than or equal to 0.95. So we're basically looking for something here, right, that ensures that this region is at least 0.95. Okay. So if you look at the table, right, 0.95 lies somewhere in between 1.64 and 1.65. And I'm going to use 1.65 to be conservative because we want this region to be at least 0.95. So 1.65 works better here. And so we want this thing, right, this here, which is going to be 200 over square root of n, square root of 9n, to be bigger than or equal to 1.65. So n here is going to be less than or equal to 200 over 1.65 squared 1 over 9. Okay? So if you plug this into your calculator, you might have a decimal in there. Then we just pick n, the largest integer that satisfies this. Okay? So we can plug that into your calculator. You'll find that it's going to be 1632. So that's part B. All right, last part. Let n be the first day when the total number of gadgets is greater than 1,000. What's the probability that n is greater than or equal to 220? Again, we want to use the central limit theorem, but the trick here is to recognize that this is actually equal to the probability that the sum from I equals 1 to 219 of xi is less than or equal to 1,000. Okay. So let's look at both directions to check this. Right? If n is greater than or equal to 220, then this has to be true. Because if it weren't true, then, and if this were greater than 1,000, then n would have been less than or equal to 219. So this direction works. Right? The other direction, if this were the case, it has to be the case that n is greater than or equal to 220. Because up till 219, it hasn't exceeded 1,000. And so at some point beyond that, right, it's going to exceed 1,000, and n is going to be greater than or equal to 220. Okay, so this is the key trick here. And once you see this, right, you realize that this is very easy because we do the same steps as we did before. Right? So we're looking for this, right? This is equal to, again, you do your standardization. So this is from 219, and you get 5 times 219 for the mean, and 9 times 219 the variance. This is less than or equal to 1,000 minus 5 times 219 over square root of 9 times 219. Again, you can do the half correction here, make it a 1,000.5, but I'm not going to do that in this case for simplicity. Okay? So this is approximately equal to z being less than whatever this is. And if you plug it in, you'll find that this is negative 2.14. Okay? So in this case, we have, this is the probability that z, again, we do the same thing, is greater than or equal to 2.14, right? And this is 1 minus probability that z is less than or equal to 2.14. And that's just phi of 2.14, 1 minus phi of 2.14. And that's, if you look it up on the table, it's 2.14. It's 0.9838. Okay? So here's your answer. So we're done with part C as well. So in this exercise, we did a lot of approximate calculations using the central limit theorem.